So always share. Okay. So you can see a Jamboard or something. I don't know. Yeah.
Right here.
Yes.
Okay. So, well, so the idea was to tell about our work on, how they call it, Weisfeiler Leman algorithm. Okay, this is hard. Something. Well, so this is actually a family of algorithms, of polynomial time algorithms that are meant for checking whether two graphs are isomorphic. And like, okay, we know that none of these algorithms actually always, none of them works always. But still, and actually it wasn't trivial to see. But still, there are like many connections to different things. And so I will start like by explaining what it is and what are connections. And then like our own work is about to see the power of this algorithm on specific graphs that come from sets of points in Euclidean space. So
but you say algorithms, it's just hash code, right? And it's to see whether two graphs are not isomorphic.
Yeah.
Okay, yeah, okay. I got
well, I mean,
yeah.
What did you say? Hash codes or
It's just hash code, like it maps graph to a number. And then if the two numbers are different, you know that the graphs are not isomorphic. So it's hash code that is invariant under isomorphism.
Yeah, one might say that. But okay, but let me.
That's in network X. It's famous package Python for dealing with graphs, and you can just ask for this hash number, and it's very useful in many places. Okay, sorry, I will not interrupt. Let's
Yeah, I mean, I'm not sure that that's what I'm exactly what I want to. So, but like, so actually, there will be a family of algorithms. There will be like one WL, two WL algorithm, and so on. But I will start with this one WL. It's not really impressive. Its power is not really impressive, but still. And then I will tell like what are different characterizations for every WL, but let's start with one WL. So how does it work? So the idea is very natural. Okay, so we have two graphs and we want to check if they are isomorphic. Well, the first thing, okay, we want to check whether they have the same number of nodes. Okay, but what next? The next, we can look at the degrees of every node, and then then we can look at the multi-set of degrees. Meaning that, okay, if both graphs have the same number of nodes of degree 1 and the same number of nodes of degree 2 and so on, then okay, if they don't, then they are definitely non-isomorphic. But if they do, okay, there is some chance. But okay, but that is what I'm described you is basically the first iteration of that algorithm. And to see what happens next, okay, so in general, in that algorithm, we start, so we have two graphs, and in each moment we have two labelings of the nodes of this graph. So initially, like, I don't know, every node obtains the same labeling. I don't know, call it A. And then we just check like at 0 iteration, we just check that we have equally number of equal number of nodes. Then in the second iteration, what we do, we look at the degrees of the nodes, but it can be seen that, okay, I look at my node and I just like consider a multiset of the labels of its neighbors. Well, multiset, it means that, you know, if I that the elements are with multiplicities. And then after the second iteration, okay, let's draw something more interesting. Like, so like the labels after the first iteration will basically be, every node will be labeled by the degree.
So in each iteration, you replace the label of the node by the set of labels of its neighbors.
Yeah, but not only the set, but multiset.
Multiset.
So let's do some example. So like if we have a graph on the left, right? So okay, there are 2 nodes of degree 3 and 3 nodes of degree 2, but that's just after the first iteration. And then, okay, well, what will be, let's say, with this node that I'm highlighting, after the second iteration, its label will be now, we go through all its neighbors, there are 3, and we collect their labels from the previous iteration, and then, so this will be like a multiset 3 to 2. So it basically, it says that, what does it mean? What does it says? This multiset tells us about the node. It means that there are 2 neighbors of this node of degree 2 and 1 neighbor of degree 3. Yeah. And then, okay, so in this particular case, like after the first iteration, we distinguish these graphs, right? Because they have different degrees. But if not, we continue in this way. And like, and after each iteration, we check if like every multiset of this form appears equally many times in the left graph and in the right graph. And if not, then we know for sure, well, it's more or less obvious that if 2 graphs are isomorphic, then in every iteration, like everything will be the same. Every label will appear equally many times. But the algorithm, okay, and there are 2 things why, okay, like when we stop, and one thing is that, okay, how we store this, if we want to
Sasha,
perform this algorithm. Yeah,
I'm a bit worried the algorithm is not clear. Because the first iteration you explain in a different way. When you write 3, so you start with all nodes having the same label A, and then you write 3.
Yeah. So
you means this multiset containing 3 times the element A.
Yes. I'm just kind of that's what I meant formally, right? So, but yeah. Okay, so the multisets after the first iterations will be just like, you write it like in 2, it means you have a multiset with A multiplicity 2 and so on.
So in the kth iteration, you represent the graph as k nestings of multisets. So the
yeah. Well, I mean, but one point is that, okay, but it will be very inefficient to store these multisets throughout the algorithm, the whole algorithm.
Yes, because after k iterations, n to the power k if you have n nodes, and therefore you can sort. And I guess the algorithm just sorts multisets all the time.
Yeah, or it just, I don't know, it encodes them each time. You have like n multiset, well, I don't know, it must 2n different multisets, and you just rename them by using some natural numbers from 1 to n, like equal multisets in the left and the right should be named by the same letter or something.
Yeah.
And then you start again, and then you obtain new multisets and you rename them, you know, so that at each moment there's like only polynomial memory unit, so no problem. So, and then the one thing, okay, but okay, in principle, they're like, you can do infinitely many iterations. But, and we say that two graphs are indistinguishable by this test if after any number of iterations, each multiset, each labels appears equally many times on the left and on the right. But the other thing to understand is that we actually like have to do at most n iterations to understand that. Well, will we ever find will we ever distinguish these graphs? And the point is that so why is that? Because
okay, but so Sasha, you should not explain why, because if you understand algorithm, it should be obvious answer.
Yeah,
so
then
somebody
say
can answer why is it true that after n iteration, if graphs are not isomorphic after n iteration, you will have a different representation of a graph.
Well, sorry, I don't understand. So if the graphs are not
different,
isomorphic, then it's not a complete algorithm for checking isomorphism, right? So
oh, sorry, yeah, I made a mistake. Yeah, sorry, yeah.
Yeah, so okay, so it actually requires something to say that we can only check the first n iterations, and if everything is the same after the first n iterations, then it will always be the same.
So
why is that? Sorry?
Why is that?
Why is that? Okay, so the idea is that, okay, we have a sequence of labelings, right? So if you start with the labeling with everything the same and so on, but the idea is that each time the new labeling, so I mean, so what will happen is that what I initially, like, I have all nodes are in the same equivalence class with the same with respect to this relation, and then we will just, what will happen is that, okay, some nodes will be equal, and what will happen is that maybe some equivalence classes will be divided into smaller ones. So formally, it means that if I have, if I know the labeling of the node and in some iteration, after some iterations, then I also know its labeling in the previous iteration. So each new labeling uniquely determines the previous labeling, right?
Okay.
And so, do you see why is that or not?
No, I think, for example, on the second iteration, you just compute the number of nodes of each time. If you just add up that numbers, you
Yeah.
update the degree.
Yeah, like, okay, so yeah, yes.
And the third iteration, I guess the same. You need to add up something to obtain. So can you explain what happens? Why is
Yeah,
it?
so you have to show it, well, by induction. So in the beginning, like, what you have after the first iteration uniquely determines what initial labeling, because initial labeling is just the same for all the nodes, so it's trivial. And then, okay, you have some node and you have some, it's labeling G I plus one after I plus one iteration. And by definition, it's just a multiset of labeling from the previous iteration from its neighbors. And you have to show that this thing determines just the labeling of U after iterations. And that's because, okay, these guys uniquely determine Ci minus one of P. And then we use the induction hypothesis to say that the multiset of these guys uniquely determines.
Sorry, I don't understand how you restore the color of U by the colors of neighbors.
The color of U by colors of neighbors.
Yeah.
So I'm in the process of explaining that, no?
Okay, but you
mean,
go to I minus one iteration.
Yeah, I mean, by induction hypothesis, he I plus he I of V uniquely determines he I minus one of V.
Okay.
And then if I know the multiset, so it's like some labels after I iterations, then I also know, I just apply this function which gives me labels after I minus one, and I obtain the set of labels after I minus one iterations over my over the neighbors of U, right? And this multiset is by definition is just the label of U after I iterations. No?
I think it's obvious.
Yeah. So I don't know. Any doubts?
But how you restore the label of U?
How I store the label of U?
Yeah,
well,
you are speaking about labels of neighbor.
Yes. By definition,
but it seems that you can
the label of U after. How do I store the multiset or what?
The label of
so
U.
I mean, so this is just
the
a
label
definition,
of U
right?
After I iteration is just the multiset of labels of neighbors in
After I minus one iterations.
Yeah, okay, it's really obvious. Okay.
Yeah.
But maybe
Okay.
it's confusing because you write parentheses twice. I guess when you write multiset, you do not need to write parentheses twice.
But if I write that just once, then it will be just sets. I mean, we have to agree on some notation for multisets, I guess.
Let's use the usual notation as for sets. Why not?
Because multisets are not sets. Okay. And Sasha uses this double parenthesis to stress that he speak on
okay, so that confused only me. I see now.
Yeah.
Okay.
Yeah.
Or other
actually,
people
I don't know this
silent,
notation, but it's quite natural. Okay.
So it's not that, okay, let me try. It's not that I have a set and then I consider a singleton set consisting of this set. It would be confusing for mathematical logicians, but it's just, it's just a notation for the multiset.
Okay.
Sorry.
Good. Some
notation. Yeah, and then why I was explaining all of this to show that I need to look at n iterations. But now you see that so these labelings, each one of them, each next one, each subsequent one kind of is finer. So they are more fine and more fine and more fine. So at some point, like, so the number of equivalents, like classes with respect to these labelings, which means that two nodes have the same labeling, can only increase, but it cannot be more than n. So after n iterations, I will kind of get a fixed point. So I will have some, after at most iteration, I will have a labeling, and the next labeling also. So I have so what I will explain that. So after some.
Sasha, I think that, again, this is obvious. If at each time you divide some class of equivalence into two classes, then after n iterations, all the classes become stable, right?
Yeah.
Yes. And then it's just important that when they become stable, and the next iteration and all of this the same, and then this process will repeat itself from on and on.
Yes.
From now on infinitely many times. So you have to just check the equivalence after an iteration.
The labels can be changed after that step, but still the classes of equivalence remain the same.
Yes. Yes. So it gives some polynomial time algorithm for checking isomorphism. But okay, this is one WL, and there is like very
sorry, I have a question.
Yeah.
I heard that this algorithm can be released in time n times log n. Do you know this nice realization?
In n times log n?
Yeah. I forget the exact reference, but it is in my mind. I forget the exact reference, and so the question: do you know this result? If not, maybe it's false.
I know some other results where there is also n log n, but that doesn't sound different. But okay.
Okay, so sorry. Maybe.
I mean, my concern is that even to store a graph, we need n squared, but I don't know in general. So. I mean, the input data is of size
maybe n means the number of edges of graph, because actually you need to look at all edges in graph for sure.
Yeah. Well, I don't know how to do this in linear time.
Okay, so let's keep it.
Yeah. So okay. And okay, so there is an example where it fails, and it's very discouraging one, but nevertheless there are other algorithms, the high family. So one is just two triangles and a hexagon. So the problem is that okay, they are so like these two graphs are obviously non-isomorphic, but the point is that just after so what happens in both graphs, just after the first iteration, every node has degree 2, and then we already have a fixed point and everything is the same. It's a fixed point, and so these graphs won't be distinguished. So okay, but then there are still, you can ask even about 1WL. So which graphs cannot be distinguished by that? Can you
are equivalent under this relation? Just colorings are the same.
Yeah, and it turns out that there are like 4 characterizations, and they're interesting, and then some of them generalize to other algorithms from the family that I didn't yet specified, but I want to state this characterization in that simple case and maybe prove some easy directions. And then I will define the general algorithm, the family, like general case, and how the characterizations fail. So, okay, so there is a, okay, I know. So the theorem, okay, so we have two graphs. And then we want to say that, how would say that they are like equivalent from the viewpoint of this algorithm, if and only if. Okay, well, okay, so we want to say that some conditions are the same. One condition is that the graphs are equal. The other condition, let's say, is the following one. Is that for any tree T, there is the same number of homomorphisms from T to G1 and from T to G2. And by homomorphisms, I mean that the edges should be preserved. So if I have two nodes A and B, and they are connected by the edge, then there must be an edge between their images.
But not the other way around.
But not the other way around necessarily.
And what do you mean here by tree?
By tree, I mean just
Three.
undirected tree.
Three.
I say
Graph, connected graph without cycles.
Okay.
And okay, so and to put it into a context, so there is a lowest result that okay, two graphs are isomorphic if and only if there is the same number of homomorphisms, not just for trees but for all graphs. And one direction is obvious. If two graphs are isomorphic, then obviously for any graph there is the same number of homomorphisms from this graph to G1 and to G2, but the other is not. And so in the sense that now it's kind of, we see now that this equivalence relation, which gives us given by one WAL algorithm, is kind of is a weakening of that. So you get this equivalent relations if instead of all graphs you consider homomorphisms from just the trees. Okay. And this is one correct. Well, okay, this is one characterization that I know.
By the way, Sasha, is it true that there is a homomorphism from G1 to G2 and also a homomorphism from G2 to G1 when they are isomorphic?
Yes, because I think well, first they must have the same number of.
Why no? No, not the same number.
I mean,
homomorphism can glue vertices. It's not injective.
So we consider here non-injective homomorphism, right?
Yes.
Yeah, non-injective. So I guess
it's important.
yes. So let me think. So I guess then the answer is no. So if we have a homomorphisms,
Actually, any two-colored graph have a homomorphism to one edge graph.
Or to empty
yeah,
graphs
every
of
And
sizes.
so if G1 and G2 are two-colored, then there are homomorphism from G1 to G2 and from G2 to G1. But there are non-isomorphic two-colored graphs, of course.
sorry, so
Or
what's the
one
example
colored
once
graph.
again?
I mean
know,
that
just-
proper coloring of a graph is just a homomorphism to complete graph.
Yes.
It's easy to see. So if graph is two-colored, then there is a homomorphism to K2, to one edge graph. But one edge, if G sub 1 and G sub 2 has at least one edge, then there are homomorphisms from each other. Homomorphism is not assumed to be injective or surjective in general, and you define it in this standard way.
But I don't know. Well, let's say I consider this triangle and this two edges. Then I have a homomorphism here because I have this like but not the other way around. No.
Yeah, but one of them is two-colored and the other is not.
Yeah, but I don't have a homomorphism from here to here. No.
Yeah, but try two colored graphs. Yes, two bipartite graphs.
My claim is if you have two non-isomorphic two-colored graphs, then there are homomorphism in each direction.
So if I have bipartite graphs,
Yeah.
yeah. I mean, then you just.
I just sent all vertices in the ends on one particular edge of the graph. It will be a homomorphism.
Okay, the answer is clear.
Okay, sorry, and
Okay.
one more question just to clarify. Am I right that a bijective homomorphism is not an isomorphism? Yeah?
No,
So,
because here is a counterexample, like this one.
okay, yeah, I understand. So we need that the
Yes.
inverse result to make two graphs isomorphic. Okay, thank you.
Yes. Okay, well, let's understand. Okay, I can try to show there's one simple direction of the fact that these two conditions are equivalent. Namely, if the graphs are equivalent from the viewpoint of 1WL, then they have the same tree, number of homomorphisms from trees. And to understand, yeah, the idea is that okay, so first there's so I'm showing that like from 1WL the same number of homomorphisms, and the idea is that okay, so first we have to understand, we have to say like what are the labels. There's a nice point of view on the labels that arise during the algorithm. More specifically, I claim that the label after E iterations can be identified with the just the tree of the paths of length I from this node. So, I mean, what is the tree of the paths? Well, you have the set of all paths, and you just of length at most I, and you can just arrange them in the tree with respect to the relation with the extension relation. So, like, what does it mean? So if I have a graph, I don't know, something like that. Okay, what is just the tree of paths of length 1 at this node? It's just this thing, right? Well, we have two paths. And by paths, I mean paths, not necessarily simple paths. So in particular, so what happened? What is the tree of paths of length 2? So they, in the first step, they can go either here or here, but then, okay, I can, let's say from here, I can return here, or I can go here, or I can go here. So it will be this and the same for this. And imagine that, okay, so when we see that indeed, like this tree after the first iteration, it can be identified just, we just need to give the number of neighbors, and this is the degree, right? So this equivalence between the trees of paths and the labels, if one WA algorithm falls after one iteration, then we just have to...
and can you write, please, now the tree for the rightmost node so that we see that it's different?
For the
rightmost node.
For this one, right?
Right, for this one.
Okay, so each path goes either here or here. And then if we went here, then we have two options. Boom. And here we have three options.
So this is boom, that boom, these boom. Are different trees.
Yeah, these are different trees, and they correspond to the labels, just because. Okay, what happens in some iteration of the algorithm?
Yeah, it's quite clear.
Yeah, so let me just say that we just collect the trees of paths of the neighbors, and it gives us a tree of paths of larger depth, right? Of depth 1. So in other words, it means that two graphs are the same if and only if I take any depth and consider the trees of paths of that depth, each tree appears the same number of times in one graph and in the other graph. And then we have to show that this implies that for any tree T, which doesn't have to be just any tree T, there's the same number of homomorphisms to one graph and to the other graph. And this is more or less obvious. The only thing we have to realize is that, okay, well, we can take T and we can fix any node of it. And then, okay, our homomorphism should map it somewhere in my graph. But then what I claim is that, okay, and then I can count the number of homomorphisms that map my indicated node U to that node. And I'm claiming that this just depends on the tree of paths that grow from this node. And if we realize that, it means that the number of homomorphisms to both graphs are the same.
Because each such homomorphism is a homomorphism in that tree. And we just
can be extended to the tree, because, okay, well, the idea is that, okay, we then have to put these two nodes to some neighbors of that node, and then these two guys we have to put to some neighbors And this is all just to specify this homomorphism. You can instead specify homomorphism to the tree of paths, and this will be the same. I mean,
yeah.
The homomorphism is not injective.
Yes, but
yes, but we
the
go
tree of
so
paths
we-
gives us a possibility to define a non-injective homomorphism.
But
Yeah.
Bruno, the point is that if we know the image of the root of the tree, that all the other nodes in that tree should be mapped to nodes in that tree, a tree rooted at that image of the root. And so we can't use any different nodes.
Yes, I understand, but this criterion B, it is any homeomorphism of only injective homeomorphism.
on
Oh,
any.
Any, okay, so now I understand. Okay.
But,
Okay, great.
but we have proved this, I guess, also for injective homomorphisms. The number of them is also the same, right? Am I
Yes.
right?
No, but the example
well, I
with
don't
two
know.
triangles.
No.
No.
Why not?
Counter example is two triangles and the sext
Yes,
from
of
previous
course.
slide.
Hexagon.
Yeah, hexagon, yeah.
So
And you say that
So a path of length 4.
Yeah, half of length actually. Yeah, four. Okay.
but
well,
when,
yeah, so it has. Can you hear me, by the way?
I'm here.
okay,
Yeah,
what
sorry, I mean-
about the path of length
Yeah.
4?
And the path of length 4 has 0 injective homomorphisms, right, to the triangle,
But
but it has a homomorphisms to the hexagon. And why they are the idea is that why the argument doesn't work for injective homomorphism, because an injective homomorphism to a tree of paths doesn't give you an injective homomorphisms to the initial graphs. So there is no this equivalence. So we have to count all homomorphisms. And the idea of the other direction, how to show it, it's less trivial. So we have to show that
Wait, Sasha.
Yes.
So you said that what is the statement of the theorem? I'm confused now. Can you return?
So yeah, so the statement of the theorem is that these two conditions are equivalent.
So G1 is VL equivalent with G2. I thought if either one of 4 conditions hold, G1 equals G2. Oh, so you're gonna give.
Sorry,
4
I mean, sorry,
criteria.
there are like 4. I didn't say the other 4 conditions. I mean, these are 4 equivalent conditions. Each of them are equivalent, and I just stated
okay.
2. So, and A and B are equivalent.
Okay,
and the idea of the other direction is we have to show if every tree has the same number of homomorphisms, then every tree of paths appears equally many times. But it's actually like a system of linear equations, right? Because what we did is that the number of homomorphisms from T to G1, you wrote it as the sum of overall nodes, and then the contribution of the node of V is determined by the number of homomorphisms from T to the tree of paths of V. And the idea is that, okay, any possible, then we can take, in this sum, we can just take all possible trees of all possible trees and count how many times they appear in that sum and multiply by the number of homomorphisms from T to that tree of paths. And so this will be like a linear system where the matrix is given by, where the elements of the matrix are the number of homomorphisms from some trees to other trees of the same depth. So you can consider like the matrix where you have all trees of some fixed depth and the number of homomorphisms, and the element is the number of homomorphisms from one tree to the other tree. And the point is to show that this matrix is invertible, and then we will have the other direction. And to show that the matrix is invertible, there's a nice argument, some strange argument. You show that it can be presented as a product of upper left triangle matrix and the lower left triangle matrix. And it comes from the ideas that we can present each homomorphism in two steps. First, we can indicate the image of the homomorphisms, and then inside of this image, the homomorphism will be injected. So, and then this presentation will present two matrices, one of which is lower triangle and the other is upper triangle. Okay. Well, I wanted to give some idea how to show the other direction. But I wanted to also state two other characterizations. One of them, okay, let's start with the logical characterization. So the characterization would be that for two graphs, they satisfy the same statements of some form holds in both graphs. Namely, this will be what they call, I think, C2 logic. And this conditions that for all statements from this logic, they they hold in G1 if and only if it holds in G2 is equivalent to 1 WL equivalence. And what is this logic? In general, so it's just almost ordinary first order logic, and we have well, we have equality, I guess, and we have a adjacency relation. So given two nodes, there is a predicate that and I mean the support is the set of nodes, like where our variables range. And then we have quantifiers and logical operations, but the only thing is that we have counting quantifiers. The only difference is that we have counting quantifiers is that, so we can write that there exists at least two x's that satisfy, two different x's that satisfy something.
So for each k, we can write a quantifier. There is at least k, right?
Yes. So for each k, we can write, yeah.
So we enrich
yes.
the first order logic by adding these quantifiers. So if they are equivalent in that logic. They are indistinguishable and the other way around.
Yeah, but
For
what 2
example,
stands for?
we can, say it again, what means 2?
2 means that we can use only 2 variables in our formulas.
Ah. Yeah, so,
But we can use,
can we reuse variables?
they can be re-quantified, yes.
Uh-huh.
But
Nice.
like in the syntaxes, you only have X and Y.
Mm-hmm. Mm-hmm. Ah,
And
so
now I can already
that's
state that like,
that's very strange.
Yes, yes.
That's incomparable to ordinary first order logic because of this restriction about variables.
yes.
I'm sorry, I don't understand this counting quantifiers. It seems that quantifier, there are at least 2 different can be expressed. You have equality relation, and it is can be this quantifier is just equivalent to quantifier
Misha,
that exists.
Yeah, but the whole point is that you can express it, but you need more than 2 variables for that then.
Ah, got it.
If you want to
Yeah.
use at most 2 variables, but
Nice,
still express this quantifier.
nice. Yeah, you are restricted in the number of variables in the formula, so this counting quantifiers are.
so Misha has explained that actually it's weaker than first order logic because you can express in the first order logic that quantifier, so that's weaker than first order logic.
Yeah,
Yes,
but,
it's weaker, of course.
It's some fragment, but it's just nice that we can just say that this is like equivalent to that 1 WA. Like 2 variables are equivalent to 1 WA. And I just say in advance that there will be equivalence, like 3 variables will be equivalent to 2 WAs that I didn't define, and so. If you fix the number of variables you can use, you have some algorithm which expresses, which has exactly the same power as this logic.
Mm-hmm.
And to understand, okay, so again, one direction is simple here, and I guess the simple direction is that if graphs is from C to A, where A, recall it was our equivalence with respect to 1 WA. If graphs cannot be distinguished by the logic, then they cannot be distinguished by that algorithm. And to show that, well, I mean, I think it can be shown by contraposition. So if they can be distinguished by the algorithms, then they can be distinguished by the logic. And the whole point is that in that logic, I can express for a given node X, I can write a formula which encodes the tree of paths of the certain length that grow from this node. And let's try to do it just by an example. So I don't know, we have something like that. I don't know, let's consider the following graph. So now if I look, if this is X, then what is this tree of graphs? It's just this and this. One node has 1 neighbor, the other node has 2 neighbors, and the other has 1, 2, 3 neighbors. Okay, yeah, so one point in that logic is that you can, instead of this, there exists at least two quantifiers. You can write that there exists exactly 2 without increasing the number of variables, because you can just write in parallel the statement that there exists at least 2, and it's wrong that there exists 1.
Mm-hmm.
Okay, let's try to do this. So, okay, so I have X and I want to write using at most two x and some other variable y, a formula that encodes me this tree. So first I write that there exists, well, at least 3 y's. Such that they are connected to x. Well, okay, let's just do a simpler thing where we have a quantifiers where the statement that there exists exactly 3 different y's, exactly 3 quantifiers, the simple case. And first I write that there exists. No, sorry. This is kind of not so instructive example. So let's modify it. So let's add this, and then I have my G of paths, then my X has 2 neighbors of degree 2 and 1 neighbor of degree 3. Okay, and then I want to encode the number, this tree. So I want to show that, okay, there exists Y which is connected to X which has degree 3. So I can write that there, and such that okay, I hope there exists exactly 3, and then I reuse X to show that Y has degree 3. So here I wrote that, okay, I have my initial X and it has a neighbor, exactly 1 neighbor whose degree is 3. And the point is that I reuse X on the next step, so I don't decrease the number of variables. Don't increase the number of variables, it's just 2. And then I also add that there exists exactly 2 y's that are connected to my X that have degree 2. And this corresponds, I encode these 2 guys, right? And again, this just, I use 2 variables. And then I guess I have to write something which says that I have no other. Then I can write that the degree of Y is 3 to show that there is nothing else in my tree. Yeah, and to get rid of this exactly 1 quantifiers, you just write that some statement holds at least for 1, and then you wrote a negation that it holds. Well, I mean, if it holds for at least 2, and the negation that it holds for at least 3. Okay, I don't know. So was it? Was it clear or not?
I think I understood.
I think that's clear, and we can skip it because it's very plausible, and I guess everybody can write a formula after some thought.
Yeah.
For each
Yeah.
statement like that.
So the idea is that when you go down on that tree, you just reuse the variable that was on the previous step. Okay. And okay, and the fourth characterization is via so-called fractional, or I don't know, fractional isomorphisms. And it's kind of, it will be
Sorry,
a
but
randomization of
the previous direction, you didn't explain the other direction. Why a formula exists? So why if for all because
the other direction is complicated.
Yeah, I mean, it's not that, it's kind of you have to check that if you have a formula, then I don't know, with one free variable, then basically its value just depends on the tree of paths from that formula. And if you have a formula with two free variables, it depends like what are their trees of paths and whether they are connected or not.
Okay, so it is difficult.
And if you have this statement, you just check it by induction on the formula, and then it follows that if there are equal number, every tree appears equally many times, then you cannot distinguish your graphs by formulas.
Okay, let's continue.
Yeah, and the fractional isomorphism is what? Okay, let's write the usual definition of just an ordinary isomorphism. It's just, so if I have two graphs, this is some bijection sigma from the set of nodes of one graph to the other graph, such that for every A and B, A is connected from here, right? A is connected to B in one graph, if and only if their images are connected in the other graph, and sigma is bijection. The idea is that we can, the idea is now considered like randomized bijection, so like a distribution over bijection with some conditions. But then so let me try to give a definition. So let sigma be a random variable which is distributed on the set of bijections from the set of nodes of one graph to the set of nodes to the other graph. And we say that this is a fractional isomorphism if the following false: if for any A from one graph and for every B of the other graph, for every node of the other graph, what you can do? Okay, you can take A, it's a fixed node, but you can apply sigma to A, and then sigma of A will be a random variable. Then you can look at the probability that sigma of A is connected to B in the right graph in W2. And then you can also, what you can do, you have a fixed B, you can look at the apply sigma to the one to B. And then again, it will be sigma to the -1 of B will be random variable. So, and then you can look at the probability that A is connected to the preimage of B. And the definition is that this probability should be the same for every A from the left and for every B from the right. And this is so this is what's called a fractional isomorphism. Okay, let's first.
For example, if sigma is concentrated on one isomorphism, then that's true, because this probability is either 0 or 1, depending on whether they're connected or not, right?
Yeah, because yes, if sigma is just an isomorphism in the usual sense, so it's just deterministic isomorphism. So whether these two are, so because this is also sigma and this error is also an application of sigma. So you have an edge here if and only if you have an edge here. And this is kind of a sensible randomization of this definition, because if you try to randomize this, it would be strange, right? Because there's on the left side you have something deterministic, and on the side you have something probabilistic. So you have to like put once the sigma to the left, and then you. And okay, and the statement is again that two graphs are 1WL equivalent if and only if there exists a fractional isomorphism between them. Okay, so and
can you illustrate this with example of two triangles and hexagon? What is the distribution over bijections?
It's just uniformly random.
Okay, uniformly random bijections, and it works.
And okay, so let's try to understand why that works. So it's just to take uniformly random bijection. Yeah, and I fix any node here and any node here. And then the probability, okay, then what will be the distribution of sigma -1 of B? Just a uniformly random node.
1/3 in both cases.
So 1/3 in both cases for every node.
Yeah. Okay.
And that's exactly how you can construct, if you know that, so in one direction, which is easy kind of, is that if you know that two graphs are 1WL equivalent, then you can construct this isomorphism. And the idea is that how you construct it. So you have two graphs and they are 1WL equivalent. It means that after any number of iterations, you know, these trees of paths appear equally many times. So, and it also implies that, let's say, if you consider just trees of infinite paths, right? Each infinite tree will appear equally many times on the left and on the right. And this equivalence means that, okay, I have some nodes here that have this tree of infinite path, and I have the same number of nodes here, 5 that have this tree of infinite paths. And my idea is that I will just map randomly, I will just consider a uniformly random bijection on each of this equivalence class. And it holds because they are 1W equivalent, so these equivalence classes have the same number of nodes, and I can consider a uniformly random bijection. Okay, so why is this work? This is more or less the same thing. So, but okay, let's see. So I can take any node here from some equivalence class and some node B from here on the right. And then, okay, so, and now I'm interested, let's say, in the probability that A is connected to the pre-image of B. But what I know about B? I know that B is distributed uniformly on the set of nodes in the left graph of the same, that have the same equivalence class, so the same infinite tree of paths, let's say. But okay, but okay, so this means that the question is how many neighbors of A have this specific tree of infinite paths as TB. But this is determined just by the tree of infinite paths of A, right? So I just look, so this is a tree of infinite paths of A. and I just look how many of them have the same infinite tree as B. So this probability is just what? Is just, there is sigma minus 1 of B is just a uniform distribution on the equivalence class of B. So I divide by the number of nodes in the left graph that are equivalent to B. And in the left, I have the number of nodes, how many of them are neighbors of A. But you see that this numerator is the same for all nodes that are equivalent to A, right? Because equivalence to A means that they have the same trees of infinite paths, and this tree of infinite paths from A determine how many neighbors have the same tree of infinite paths as B.
Sasha, and does it imply that if all the equivalence classes have, are singletons, then the graphs are isomorphic?
Yes, yes, but it's more or less it's easy to see without this theorem, just because
It's an exercise, I guess.
Yeah. So, and the other probability here is that I'm taking the probability that B is connected to the image of A, and again, sigma of A is uniformly distributed on the equivalence class on the set of nodes on the right that are equivalent to A, and the probability in the numerator, we have the number of neighbors of B from this of B. How many nodes, if I take B, how many neighbors of it are equivalent to A? And then, okay, I have to show that these two fractions are equivalent. And the point is that the idea is just, okay, why is that? Because if I multiply this thing by this thing, what it will be? First, I take the number of nodes that are equivalent to A and multiply it by the number of nodes, and for each of them I multiply, I take the number of neighbors that are from the equivalent class of B. So this product will be just the number of ages.
Sasha, wait a second. You multiply two terms that only depend on A, right?
No. Okay, okay. So what I have here, on top I have the number of nodes that are equivalent to B, and here I have the number of nodes that are from the equivalent to B that are neighbors of A.
Ah, sorry.
And I mean, of them, I should write the number of the number of nodes that are equivalent to A that are neighbors of B. So now I multiply the number of nodes that are equivalent to A, and for each of them, I take the number of nodes of their neighbors that are equivalent to B.
Mhm.
You're saying
And
that
this
the
is
number of edges between these two equivalence classes can be expressed in two ways.
yeah, that's just
Mhm.
it.
Mhm.
Ah, I see.
So this is how it works.
Mhm.
Okay. Yeah, so what can I do? Okay, so now we have the, okay, the other direction is again less obvious, but let's talk about now how the other WL works. So I mean, I have about 10 minutes, so we can try to discuss this. Let's say how 2WL works. Now it works as follows. So now instead of labeling nodes, we will label pairs of nodes. So we will consider a sequence of labels, and each of them will be from v squared to somewhere. And it's defined as follows. So now it's, before that, like the initial labeling was just trivial one, we're just one value. Now the initial labeling, what we have, we obtain the pair of nodes, and we have to say how the graph is arranged on them. So there are like three possibilities. One is that, I don't know, if this actually two equal nodes, it will be distinguished from the case when they are connected but by an edge and not equal, and from the case where they are not connected but different. So in the initial labeling of the pairs, we just say like whether these two are the same nodes, and if they are different nodes, whether they're connected by the edge or not. And then the update operation, what we do. Okay, let's try to. Well, okay, first of all, for simplicity, sorry, I mean, it should be defined for a pair of nodes. For simplicity, let's remember the label from the previous step, not to argue that it can be recovered. And then what we will do a strange thing. So we will go through, yeah, I write again this W, I mean AB, and this is a pair AB. So I go through all nodes and I take the following pair. So I put C in the first place, and then I put C on the second place in the tuple AB, in the pair AB. And then I go, so for every C, so basically now what happens, let's say on the first iteration, right? So for example, I have a node I have a pair AB, and let's say it is connected, these are two different nodes, and then what happens? I just give the multiset of triangles, I mean, like multiset of subgraphs that have AB and how they arrange, right? So if I have some C, I restore information whether A and C are connected or not, and whether C is connected to B or not. And then I go through all C and
Sasha, is this function symmetric? Because psi
Yes.
0 is symmetric, so it's always symmetric.
Yes. It's symmetric. So yeah, I mean, in terms of just initially, I have like initial information which can be given by matrix, where like adjacency matrix, but I specifically write 0, I don't know, on the diagonal, like the third element on the diagonal. And then and when I take some element and want to update it, so I take the corresponding row and the corresponding column, and then I go in parallel on this row and column. I take the pair like what I have here and what I have here, then what I have here, what I have here, and I consider the multiset of these tuples. Okay, yeah, so it's maybe it's less natural, but the point is that, okay, now, and we can now define the same for every. So this is 2WL, and the difference for KWL will be just that we will cover K tuples, or we will label K tuples, yeah. And the update operation will be just we go through all C, and we put C in K different places instead of R tuple. And this gives us K labels from the previous step. We arrange them into the tuple, and then we consider the multiset of all overall possible C.
I have a question. So 2WL, is it right that it can distinguish 2 cycles of length K from a cycle of length 2K?
I think yes. So let's try to understand.
Sorry, maybe you explain before this question why these labelings are invariants of isomorphism, because at the first step you have just adjacency relation for a graph. It's obviously not isomorphism, invariant of isomorphism.
Misha,
Well,
probably we count.
I mean, we count again like this, how we have this Chi0, Chi1, Chi2, and so on, and we just count that every label appears equally many times in Chi for one graph and for the other graph. And if they are isomorphic, then we can just basically say, okay, we just permute nodes, but the order of nodes is not important because we take the multiset every time.
I see.
Just the way you go, the order where you like in which you enumerate the C's here is not important because you take the multiset again. Yeah, and okay, and then.
So basically,
Yeah,
at first step, you just count the number of edges in graph, basically, and number of vertices.
Yes. So definitely the first step is invariant for isomorphisms. And then, well, you show that, you know, the label of every pair will be the same for the image of this pair under the isomorphisms, either in any isomorphism. And this is just because, like, if you apply isomorphism everything everywhere here, and this will be the same for after I iterations, then you take the multiset, and this will be, then it will be same after I+1 iteration. So how's that? Clear or not so much?
I mean,
It's rather sophisticated. It seems that it is a usual Weisfeiler-Leman algorithm applied to some graph colored by this initial color, but
Yeah, so and Bruno says that if we now, okay, I mean, for example, okay, the fact that it can distinguish that two triangles in the hexagon is easy because here we have a triangle and here not, and we will detect that there exists a triangle after one iteration here. Because we will have, I don't know, A, B here, and that's when we will see that there is some C which is connected to A and to B, and a different one. And this we won't see here, right? And I think even if I take any two cycles and I take a larger cycle and the cycle of size 2k, it should distinguish it.
it seems quite obvious because in the case of two cycles, a diagonal pair gives a specific color after k iterations, and in the one cycle after k iterations, the labeling will be different.
Yes.
Formally, it requires some proof, but
There is actually
it's
like,
quite...
yeah, because actually 2WL can kind of detect connectedness, whether two nodes are connected in a way. You can, like if a pair of nodes, you will eventually know whether they are connected or not.
Yeah.
Because, okay, initially you see whether it's connected or not. And after, if they are connected by a path of length 2, you will see it after the first iteration. If they are connected by a path of length at most 4, you will see it after 2 iterations.
So, for example, if one graph is connected and the other is not, then they are distinguishable by 2 WL.
Yes.
And that means that there is no logic characterization for that, I guess.
No, why not?
No.
You have unbounded.
Sasha already said that the logical characterization is by using formula with 3 variables.
But
yeah, now
I guess that connectedness can't be expressed in the first order logic, whatever number of variables.
But we have a fixed number of nodes.
Sorry. That's important.
The two graphs have this. So now we have, and it's true that there is a logical characterization holds, but now we can use free variables.
I see.
And using free variables, we can write a formula that two nodes are connected by a path of length at most 2 to the k by formula with like k quantifiers.
I see.
But we cannot write the same formula which expresses connectivity in every size of graph. But if we have two graphs, fixed graphs, the same, we can do that. And and the same holds for every k. So KWL corresponds to k plus 1 variables. And there is also a characterization with the number of homomorphisms. I will say it quickly. Now we should count the number of homomorphisms, not just from the trees, But for 2WL, we have to count the number of homomorphisms from graphs of tree width at most 2. And for KWL, for graphs of tree width at most K.
Mhm.
So this gives some nice, this definition of tree width, which is a nice hierarchy.
And these conditions are
You're
indeed
just
equivalent. Yeah.
sorry.
These conditions are equivalent. Counting
Yeah, so
homomorphism from graph of tree width at most K and logical. Okay.
Yes, but I don't know about any reasonable generalization of fractional isomorphism. I have to see. Yeah. Well, I mean, and to specify, so this is all was well known. It's not our results or anything. So I didn't get to our results, but I mean, I have to finish more or less.
Okay.
Maybe you can continue next time because you